Hello everyone, welcome to lecture 21 of the online course on modern display technologies, flat panel displays. Today's lecture will be on transmissive liquid crystal displays. Here is the lecture outline. We will talk about different types of transmissive LCDs and then look into twisted pneumatic TN cells. We will also talk about the film compensated TN cells and discuss about the challenges and the importance of viewing angle. So, let us look into the types of liquid crystal displays first. So, there are basically three main types of LCDs being developed. The first one is called transmissive LCD, that basically uses a backlight. So, it can provide you high brightness and contrast. The second type is called reflective LCD. So, here there is no backlight. Okay. So, you are basically using the ambient light and the display works in reflective mode. The third type is called trans-reflective LCD, that basically combines the transmissive and the reflective modes. So, let us look into the application areas of each of these types of LCDs. The first one, transmissive LCDs, are suitable for notebook computers, desktops and TVs. There you have phase compensation films that widen the viewing angle for multi-viewer usage. Projection displays basically use high power arc lamps or LED arrays as light source, because you require backlighting for this kind of transmissive LCDs. Now, coming to reflective LCDs, they are suitable for outdoor usage where you already have bright ambient lighting. So, you are basically using that particular light itself for your display. So, you can understand it is for low power application, and for LCOS, that is liquid crystal on silicon kind of projection TVs. So, reflective LCDs have their own advantages. They are lightweight and low power, all because of the fact that no backlighting is required. However, when the ambient light conditions are weak or poor, the readability of such displays also become poor. Then comes the trans-reflective LCDs, which is best suited for both mixed indoor and outdoor environment. So, you must be having a guess right now that transmissive LCDs are good for indoor applications, reflective ones are good for outdoor usage, okay, and the trans-reflective LCDs are best for mixed indoor and outdoor environments. So, they do have a backlight and it is turned on only in the dark conditions. That means this can work only in the transmissive mode when the ambient light is very low. In the case of bright ambient conditions, it goes to the reflective mode where the backlight will be turned off. So, with that understanding of different types of LCDs displays, now let us go into the basic of how twisted pneumatic cell works. So, twisted pneumatic cell will first focus into the 90-degree twisted pneumatic cell, which is the most widely used one for LCD mode for the notebook computers. So, this is how it works. So, this is the voltage up state, which is basically the bright state. So, you can see that the top liquid crystal directors, they basically align parallel to the top polarizer optical axis. Okay. So, when you have unpolarized light, only the polarization that is parallel to the polarizer's axis will pass through, and then here the light is getting twisted by 90-degree by this twisted pneumatic crystal. Okay. So, the bottom liquid crystal director basically rotates 90-degree, which is again parallel to the bottom analyzer. So, the incoming polarized light will also follow this molecular twist and it will transmit through the analyzer. So, there is a condition for this, the cell gap product, that is D into delta n, should satisfy the Gauch-Terry first minimum condition. Now, what happens to the voltage on state? So, when the voltage is on, the liquid crystal maintains its position. So, the twist is not there. So, in that case, the director reorient, okay, perpendicular to the substrate. Okay. So, in that case, the light basically cannot pass through this particular analyzer. So, the incoming light basically gets absorbed. Okay. So, you do not see any light coming out of this. So, this is basically your dark state when the voltage is on. You can also see this from this particular figure. It shows that this is how you have your halo pixel always being displayed like this. So, you have a bright and a dark pixel. So, this is what is happening to this particular pixel. So, this pixel will not have any voltage applied across this twisted nematic liquid crystal. So, the light can actually pass through. So, your screen is looking bright, but in this case the voltage is being applied. So, the electric field is basically maintaining the liquid crystal in its orientation. So, the light that is coming to this particular analyzer is getting stopped, because here the polarizer axis and the liquid crystal director or the polarization, they are basically orthogonal or perpendicular. So, these are the transparent electrodes which are being used to apply the voltages across the liquid crystal. So, what do we see here, that the normalized transmittance T perpendicular of a twisted nematic cell can be described using Jones matrix formalism. So, what is that formalism? The general transmittance formula says that T perpendicular will be phi by x whole square into cos phi into sin x minus sin phi into cos x whole square. Okay. So, here phi is basically the twist angle and gamma is basically given by 2 pi d dot delta n divided by lambda, that is the wavelength of the light. So, you can calculate x as square root of phi square plus gamma by 2 whole square, okay, and beta is the basically the polarizer angle. Okay. So, this is the generic expression. So, the expression has a second term which is gamma by 2 sin x by x whole square into sin square phi minus 2 beta. Now, for the case of 90-degree twisted nematic cell, your phi is determined, that is pi by 2. So, in that case, when you put this value here, the expression of T perpendicular gets simplified to cos square x plus gamma by 2x into cos 2 beta whole square into sin square x. Now, the Gauch-Terry condition tells you that this transmittance T perpendicular will be 1 independent of beta, and that is possible when x equals m pi. That means, the product of distance and the change in refractive index, that is d delta n by lambda, will be equal to square root of m square minus 1 by 4. What is m? M is an integer. So, for first minima you can put m equals 1, you get d delta n by lambda equals root 3 by 2. So, when you know lambda, say you want to use 550 nanometer, so your d delta n comes out to be 480 nanometer. So, this is the preferred design point for the notebook TFT LCDs for first response. The second minima you can also calculate, that is for m equals 2. So, in that case d delta n turns out to be square root 15 by 2, that is typically used in wristwatches, and that is easy for fabrication because you have slightly larger cell gap. So, your response will be slower, and these are suitable for low end displays. So, the cell design we have seen for screens, you can optimize it at green, that is lambda equals 550 nanometer, because human eye is more sensitive or most sensitive, you can say, to green. So, here is a voltage dependent transmittance of a normally white 90-degree twisted pneumatic cell. So, here d delta n equals 480 nanometer. Okay. So, you can see that the first t perpendicular is becoming 1 when your d delta n is coming out to be 480 nanometer. Okay. So, the color dispersion, it tells you that there is wavelength dependent transmittance. However, it is not too sensitive to d delta n by lambda beyond the first minimum. Okay. And the twisted pneumatic cell also behaves like a achromatic half wave plate at that particular because it changes the polarization by 90 degree. Okay. So, when it satisfies the Gooch-Terry condition. So, this is a typical response for a 4 micrometer cell gap, where the response time is typically 20 to 30 millisecond, and the contrast ratio of around 400:1 can be obtained when you apply a voltage of 5 VRMS. Okay, and this kind of response is suitable for notebook computers and also single viewer application, where only one person is looking at it. Okay. However, there are some drawback. The first thing is that the liquid crystal director tilt will cause some kind of grayscale inversion in the vertical direction, and the viewing angle is narrow and asymmetric, especially for the vertical cases. So, in this particular figure, it shows the simulated isocontrast contour of a twisted pneumatic LCD. So, these are the one on the left, okay, is without the wide view film. So, you see the area is very small in this case, okay, for viewing. So, it is mostly like for normal viewing. So, it only provides good contrast ratio. So, this is basically the contrast. So, the good contrast ratio only when it is in the normal viewing condition, and you can see the contrast decreases rapidly in the upper viewing direction, lower diagonals, okay, and in the lower direction the contrast remains high, but that then the grayscale inversion also happens. So, this kind of narrow viewing angle is basically caused because of the optical anisotropy of the liquid crystals, and there is also off axis light leakage from crossed polarizers. The another factor could be the light scattering at the polarizer surfaces and color filters. There can be also possible effect like backlight collimation effect and light diffraction from the cell structure itself. So, what are these limitation of the conventional compensation film? So, in the on state, the liquid crystal directors in the upper half are basically reoriented along the rubbing direction with almost no twist, and in the lower half that will also have a similar kind of structure, but its director plane is basically orthogonal to that of the upper half. So, what do you want? You basically require a uniform phase compensation film, example something like a uniaxial A plate that cannot simultaneously compensate both halves of the twisted pneumatic cell. Okay. So, this is one isocontrast plot that has been shown with the wide view films. So, this is basically from the Fuji photo films. So, here you see you have a much wider region where your viewing angle does not matter, right. So, let us look into this film compensated twisted pneumatic cells. So, when you have this wide view compensated films, A pair of wide view films are basically placed on both sides of the twisted nematic cells, and each film basically compensates one half of the twisted liquid crystal layer. And Fuji Photo, they basically developed discotic discotic liquid crystal films that basically helped you widen the viewing angles of the twisted nematic cells. And the molecular structure of this wide view discotic material can be seen here. Okay. So, this is the structure of the wide view film and the employed discotic compound, which is basically PDM, that is polymerized discotic material, right. Now, let us look into the structure and the properties of this Fuji wide view film. So, the discotic material, which is the triphenylene derivatives, is coated on an alignment layer over a TAC substrate, that is basically triacetyl cellulose substrate. So, what are the key features of this discotic material? First, high birefringence should be there due to the disc like pi electron kind of structure, and it forms a discotic nematic phase at temperatures below TAC deformation temperature, and it contains cross linkable groups at all 6 sides for durability. Now, the hybrid alignment structure. So, when you see if you see near the alignment structure, this discotic materials basically align nearly parallel to the substrate surface, and small pre-tilt will exist along the rubbing direction, and near the air surface discotic molecules will align nearly perpendicular to the surface. So, this basically produces a hybrid alignment structure in the discotic nematic phase, and UV curing polymerizes the material, and it basically fixes the alignment structure. So, this is where you can see this PDM layer, which has got this hybrid alignment. This is the air surface, this is the TAC substrate, and this is where this high degree of randomness is there. So, this structure basically differs from the ordinary optical material, right. So, in polymerized discotic material or PDM layer, what is happening? The director orientation changes continuously through the film thickness without any twist, and the molecular orientation fluctuates within the layer, and the hybrid structure basically consists of the splay deformation, band deformation, okay. And the PDM layer exhibits non-zero and asymmetric phase retardation from all incident angles. Also, the TAC substrate contributes a small birefringence. Ideally, the TAC substrate should be isotropic though. So, coming back to this viewing angle discussion, this particular figure basically, as I mentioned earlier, it compares the viewing angle of a twisted nematic LCD without this wide view discotic compensation film here, okay, and this is with that compensation film. So, what you see directly by comparing is that the performance of Fuji wide view compensation film twisted nematic LCDs, okay, the performance has dramatically improved the viewing angle as compared to the uncompensated one, and the viewing angle at a contrast ratio of 10:1 basically exceeds 80 degree in all azimuthal direction. That is like a wide angle viewing is now possible. So, this kind of, what are the optical improvements then? So, the viewing angle is especially enlarged in the horizontal direction, which is really good. However, this is achieved because your dark state light leakage reduces. Okay. There are some yellowish color shift, these are the associated effects. Okay. Now, this also improves on axis contrast ratio by around 10%. So, what are the advantages of this kind of film? It improves the viewing angle without reducing the light transmittance and degrading the image quality. So, it is a very important thing. And another important modification advantage is that it requires no modification of the LCD panel process. So, the existing polarizers are basically simply replaced with polarizers laminated with this kind of wide view compensation film. And this discotic film is a cost effective approach for obtaining a wide viewing angle from your LCDs as compared to the in plane switching and multi-domain vertical alignment MVA modes, right. However, there are some limitations of this approach as well. The one limitation is that reverse grayscale inversion actually exists in this kind of film compensated twisted pneumatic LCDs, and this thing basically limits its competitiveness with the in plane switching and multi-domain vertical alignment kind of modes when you are going to use it for large screen television, right. So, these features basically enable twisted pneumatic because of this cost effective approach of wide angle viewing. The twisted pneumatic is able to penetrate a larger sized LED market or for the 20-25 inch diagonal kind of display systems. So, with that we conclude this lecture. If you have got any doubt regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.